All right, we'll go ahead and get started here. Thank you all for coming. This is our webinar on lagoon recirculation. Recirculation's been, hi, this is me, Patrick Hill here from Triplepoint. Just thought I'd show my face here at the beginning of the webinar briefly. Excited to have you here today. Recirculation's been one of those things that we've learned about over the years and taken a more keen interest in the last 12 months or so. And so I kind of want to share with you kind of what we see in it and the benefits of it and potential design and so on. So what we're going to cover today, this is me obviously in a boat doing a sludge survey. This is at a facility in Colorado, and it's actually this was an anoxic lagoon system. Well, the first lagoon was anoxic, and as you can see, there's lots of sludge on the surface, and it was very low in DO and had a lot of sludge, and so it was a bit nasty, but got to do what you got to do. I've been on many lagoons over my 14 years working with Triplepoint, and it's always been a joy and a pleasure to get on a lagoon every once in a while and do a sludge survey or anything that needs to be done. So today we're going to do a brief intro of Triplepoint for those of you who don't know us, talk about recirculation, why we might want to do it, how we would model it, how we design it, and then a few case studies as to what we've been doing in terms of recirculation here in the last 12 to 18 months. So for those of you who are less familiar with Triplepoint, we are a company that really is dedicated and focused on lagoon systems. We like to say lagoons do it better. And for us, it's both our mission and our belief and our motto. It's our mission to help lagoons do it better. And it's our belief that lagoons, when they're properly designed and functioning, that they actually do it better, that they provide better treatment at a lower cost than a typical mechanical plant. And so that's all we do all day. We just focus on lagoon systems. We're going to do, the last 12 months, we've done 45 lagoon upgrades. I believe that is more probably than any other company in at least the United States. In that expertise, we get really good at it. We understand where the problems can come, and we understand how to design around those things. The second thing that we really feel distinguishes us is the fact that we take a very tailored approach to designing lagoon systems. Every lagoon is different, so every job is custom, and we don't want to just do a one-size-fits-all. And what's key about this process for us is getting the input of the operator, of the owner, of the consulting engineer on the project, and make sure that what we design is the most optimal design it can be. And the third thing is we stand behind everything that we do. We call it the we say it, we do it guarantee. If something's not working or it doesn't get installed right, or there's problems here and there, we'll come out, we'll make it work. We really want to make sure that we have satisfied customers and satisfied lagoon owners. So we have developed a variety of systems over the years to help, aid in lagoon systems to meet stricter limits or just to improve efficiency and or capacity. And in that effort, we developed our ARE system, formerly known as our Mars lagoon aeration system. We rebranded it and redesigned it last year. It took a while. It didn't happen last year, but when it got launched last year. Followed by our nitrox ammonia removal system. This system is designed to meet ammonia limits regardless of temperature. We've observed, for example, water temperatures in our nitrox reactor of down to 0.2 degrees C, and been able to get nitrification through our reactor system. And then we've also developed a total nitrogen and phosphorus removal system. And so we really feel like with this suite of product, solutions that we can help a lagoon system meet virtually any limit it needs to meet, from BOD, TSS, or ammonia, total nitrogen, phosphorus, whatever the case may be. So we've done over 150 installations as a company over the years. I say this just to sort of establish a background and our expertise in lagoons. We do this, it's all we do all day. We've got a lot of experience with it. And, we've been honored on the Inc. 5000 fastest growing companies in the United States for 2019 to 2020. And really are honored and blessed to feel that we could do this work. And, we love doing lagoon systems and working with lagoon owners. And we just want to thank everybody for putting their trust in us. Finally, before I get into this will be put on our Lagoon University online CU PDH platform. We have 10 other modules or so on there right now. You can go log into this, get free CUs or PDHs anytime you want on demand. And this, we developed this at the beginning of the pandemic because we realized that, with the lockdowns and social distancing, that, there were going to be less conferences. And we knew there was going to be a need for education. And it seemed to make a lot of sense to develop a platform like this to help give back to all the people that put their trust in us and given us knowledge about lagoons and give that back to the community. And so we do this totally for free. We're going to put this webinar on it. We're going to put subsequent ones that we're doing this fall in our series on it and continue to build this. So I encourage you, if you ever need PDHs or CUs, that, get on this site and you can get them pretty quickly and easily. So recirculation, I kind of quipped the joke. We've all seen the proverbial pharmaceutical commercial on, do you have a problem with, Lagoon DO, algae, ammonia, BOD, total nitrogen? Are your concentrations at your effluent kind of jumping around from month to month? Do you see a lot of volatility there? Well, talk to your doctor about lagoon recirculation because it can help, and I'll get into detail on all these, but it can help with all manner of these things. And it tends to be something that just helps to improve the overall performance of a lagoon system by 10 to 20%. I actually learned about recirculation from our good friend, Steve Harris, who we partnered with on some of these webinars and also in-person training over the years. For those of you who don't know Steve Harris, he's a lagoon guru, a lagoon expert, and he often gets brought in to help solve some of the worst lagoon problems. And sometimes he's contacted by the state and the environmental regulators stateside or the EPA. I mean, he's that good. And most of the time he recommends recirculation. And so this is something that we got from him. So I don't want to claim this as ours, but these are some of the things he says, and we've come to find out the same. So what is it? So lagoon recirculation is simply a matter of just pumping water from, further on down in the process to a point further up the process. And that can vary anywhere between literally pumping water at your final pond to your first pond, or pumping water from any intermediate pond to another pond. And this concept of recirculating as a concept has been around for a really long time. Not as much used in lagoons, but in activated sludge process. They've been recirculating for many of the same reasons that I'm going to posit here to y'all, in order to get the benefits of denitrification, of enhanced ammonia reduction, enhanced total nitrogen reduction, so on. And so it's not a new concept. It just hasn't been used as often in lagoons as one might think. And I think there's just a lack of awareness about what it is and how it benefits. I think what's funny about the recirculation concept for me, and I remember talking to, and this picture shows you here, one system that we installed that I'll talk about later, is, we often recommend that people recirculate one Q, so 1 times their average daily flow. So, if they're getting 100,000 gallons a day coming into the plant, we want them to recirculate 100,000 gallons a day. And I'll explain why that is in a minute. But, often people are like, wow, that's where does the water go? So we're just circulating water within the plant. It's going around and around and around and around in a circle. It's like circular logic. and it does kind of take a minute to think about. But what happens is, your real hydraulic retention time stays the same, right? So the water doesn't stay in any one place as long as it did if you didn't have recirculation, because it's going around in a circle. It's just moving faster, right? But at the end of the day, like any plant, right, you've got water coming in and you've got a certain amount of hydraulic capacity in the plant, and so water is going to flow out. And sometimes it'll take a few days if you're going to really get the recirculation cranked up, where you won't discharge for a couple of days while the water is going back to the front, kind of catching up with the rest of the system. But ultimately, it always does. And so it's just a matter of moving that water from one place to another and basically moving it one big circle, but eventually it always goes out. So it doesn't change your hydraulic retention time. That gallon that's coming into the plant today before you recirculate stays in the plant for the same amount of time as when you do recirculate. It just doesn't stay in any one place for the same amount of time. So why? To talk a little bit more about the details around this. So first of all, recirculation can help improve DO and reduce BOD. And so, I often say I'll just tackle each one of these briefly. So with the DO, there tends to be an inverse relationship between DO, dissolved oxygen, and biochemical oxygen demand in a plant, right? So as your BOD is reduced, your DO tends to increase, right? And it makes sense. At the end of the day, it's biochemical oxygen demand with the emphasis on oxygen. So, you have the microbial community at the beginning of the plant where there's lots of biochemical oxygen demand consuming the oxygen, as you expect them to do as they are consuming and reducing the organic load. And as you move further on down the plant, right, you have less biochemical oxygen demand, and so that oxygen is just hanging out in the water column because nothing's consuming it, right? It's just sitting there. And so that's one big reason. The second big reason that you tend to have more oxygen at the back of the plant than at the front is that you tend to have more algae at the back of the plant than the front. And this reason's pretty simple. Anybody who's been around lagoons a lot will know that if you walk up to a primary lagoon, it just tends to look less green, obviously an indication of algae, than a polishing lagoon. And that's because there are solids in the water column that are preventing the sunlight from penetrating down to the bottom where algae can form and then rise to the surface. And it just prevents that growth just due to the general turbidity in the water because of the organic load in the water. So by moving water from the back of the plant to the front, you're adding DO because you've got dissolved oxygen at the back of the plant, and you would probably have less at the front of the plant. So that'll help to improve your overall dissolved oxygen levels. The second thing is BOD. So BOD is if you can recirculate from the back of the plant to the front of the plant, right, you are giving it a second bite at the apple, in essence, right? And because there's more BOD at the front of the plant than at the back of the plant, because there's just more organic load up there, right? You have a more vibrant microbial community at the front of the plant than the back of the plant. And so when you have a more vibrant microbial community, it can obviously break down that residual BOD that's coming from the back and being put into the front or closer to the front more readily. There's just more bugs to eat it, is the short answer, layman's terms to it, right? And so you do tend to see better BOD removal in systems that have, recirculation. So the second thing is algae reduction. So when we think about, what causes algae to grow within a lagoon system, we think about things like warm water temperatures in the summertime, sunlight that's able to penetrate through the water column and down to the sludge blanket at the bottom where there are nutrients, which are in essence just fertilizer for that algae. We think about mixing and thermal stratification associated with mixing, which means, it's like when you go to a lake and you jump in the lake, right? The top layers of water are just warmer, right? The deeper you go in the lake, the colder it gets, and same thing in a lagoon, right? Even with partial mixed aerated lagoons, depending on the level of mixing and aeration in them, you're going to get this thermal stratification. And so when you recirculate, you're doing a number of things. You're thermally equalizing the lagoon, so you're able to pull, let's say, colder water from the back of the plant that's near the bottom, right, and put that in front of the plant, right, and maybe you're injecting that colder water at a higher elevation in the water column, right, so now you've just raised the temperature of lowered the temperature of the water a little bit, which isn't good. Algae doesn't like that as much, right? You're then also, and I'll get onto this in more detail, but you are reducing overall nutrients through recirculation. If you're able to get nitrification, denitrification, which I talk to you next, which just produces less fertilizer. And then the other thing is you're mixing, right? And you're moving that water faster, right? And the faster you move that water, you're really dissuading algae growth, because algae really likes stagnant water. And when you increase the velocity through the lagoon system by recirculating and just making it so that water never stays in one place as long as it would have, you're reducing the potential for algae to grow, and you're not giving the algae the best environment it wants to grow in. Okay. So now to move on to the nutrient removal benefits, specifically the total nitrogen removal potential that you get with recirculation. So before I get into that, I want to talk about the different forms of nitrogen real briefly, a little chemistry class here, or biology class here, just real quick before I jump into exactly how this is done. So nitrogen has a number of different forms. One form is the ammonia form of nitrogen, which is both NH3 and NH4, ammonia and ammonium. And then you have nitrite and nitrate, and then you have organic nitrogen. So all of these things together make up total nitrogen within your system. And sometimes and we'll see this in some of the data I'm going to show you later, but sometimes there are different forms of nitrogen in different locations in the plant, right? Based on what's happening, what bugs are growing and where they're growing and where they're doing their job, right? And so, you can, if you're doing nitrification now, for example, you're not getting rid of total nitrogen. You're just simply converting ammonia from one form of nitrogen to another form of nitrogen. And your total nitrogen stays exactly the same on a mass balance basis. So just some nomenclature things. TKN is the combination between organic nitrogen and ammonia nitrogen. And the reason this number is important is because the one thing we can't do much about is organic nitrogen. We can convert ammonia to nitrate, and we can convert nitrate to nitrogen gas through denitrification, but we can't get rid of organic nitrogen, at least not in lagoon systems. We can't. And so the reason you want to take TKN is to figure out how much organic nitrogen makes up your overall nitrogen coming into the plant. And you do that by simply taking TKN and minusing ammonia nitrogen from it, and that gives you what the organic nitrogen is, right? So most plants, most lagoons that are municipal only have 2 to 3 milligrams per liter of organic nitrogen in them, but it's always good to know because that's going to be a limiting factor in your total nitrogen number. And then the other one we see sometimes is total inorganic nitrogen. So for example, in Colorado, they are starting to introduce total inorganic nitrogen limits on lagoon systems. And that is just a combination between ammonia nitrogen and nitrite nitrate. And so if you're having to meet a TIN limit for total inorganic nitrogen, you don't have to worry about the organic nitrogen very much. And I think that's pretty smart on their part because, again, lagoons can't do much about organic nitrogen. And so if you give somebody a limit for something, it's helpful if they can actually do something about it. So in order to get rid of total nitrogen, you've got to do two things. You've got to convert your ammonia nitrogen into nitrate. And in lagoon systems that are municipal, most of your nitrogen is ammonia that's coming in. And again, I'll show you some data shortly to illustrate this. And so the first step is you got to nitrify it. And we've got webinars on nitrification. I'm not going to go into detail on it here. And then once you have it in the nitrate form, you need to denitrify it, which is to take that nitrate and convert it to nitrogen gas. Poof, it's gone, like magic. And so the question is how to do that, and why would you want to do that, more importantly. So, when you denitrify, there's a lot of good things happen. I mean, a lot of folks do it because they have to meet a total nitrogen or total inorganic nitrogen limit, but there are benefits to it over and above just meeting a limit, right? Usually with a lot of these processes, meeting the limit, there's no side fringe benefits. With denitrification, there are some fringe benefits, which is maybe why you want to do it even though you don't have a total nitrogen limit. One thing is that for every 1 milligram per liter of nitrate denitrified, you get about 3.57 milligrams per liter of dissolved alkalinity in the water, right? And so why do we care about that? Well, alkalinity can be a really good thing, and it's especially a good thing for your pH, making sure your pH stays stable. It's also a good thing for nitrification, right? And, there are times in which the nitrifiers are having a hard time nitrifying because they don't have enough alkalinity. And it can really improve your overall nitrification. So you improve that first step. The second thing, and probably I think the better benefit of it, is that for every 1 milligram per liter of nitrate denitrified, you get 2.5 milligrams per liter of BOD, just poof, gone. It gets used as a carbon source in the process of denitrification, and it's essentially free BOD removal. You got to pump the water to somewhere in this recirculation process, but you get enhanced BOD removal, which goes back to that first point about BOD removal as well, is that if you are able to get denitrification, you get natural BOD removal in that process. So for some plants that, let's say, are having trouble meeting BOD limits, right? They're 10 or 15 or 20 milligrams per liter above where they need to be on the effluent, then getting denitrification is going to help you to accomplish that BOD limit. So here's the rub. The rub is that in order to denitrify, you must nitrify first, because most of your nitrogen coming into your municipal system is in the ammonia form. And so you've got to take that, get it into nitrate form, and you need to do that by nitrifying. And in order to nitrify, you need low BOD, you need alkalinity, you need ammonia, and you need high DO, right? So makes sense, right? And in order to denitrify, unfortunately, you want some of the opposite conditions. You want high BOD for a carbon source, low DO, and lots of nitrates, right? And so it's kind of like a chicken and an egg, because in order to denitrify, you need to nitrify first. But a lot of the conditions you need to denitrify are opposite the conditions you need for nitrification. So that's where the recirculation can help, right? So we developed, and this is our patented process, recirculation is not per se patented. Obviously, anybody can recirculate anywhere, but we developed a process and that really tries to enhance the recirculation in order to accomplish these things. So we have our normal lagoon process. We start with an anoxic lagoon cell on the front end, followed by aeration for BOD removal, additional BOD removal in addition to the denitrification, followed by our nitrox system for nitrifying, and like I said earlier in the presentation, at pretty much any temperature you need to nitrify at, as long as it's not an ice cube, we're going to nitrify it through there. And then we go into our recirculating pump station. And what we do is we actually blend that recirculated water with the inflowing water from the collection system. And I'll get into more detail why we do that. But essentially, it really enhances the process and makes sure that all the nitrates and BOD and everything's mixed together by the time it gets in the lagoon. It's ready to rock and ready to go in there. And we do that along with some mixing in the lagoon as well in order to promote overall denitrification within your first lagoon. So when we look at trying to answer the question of how much should I recirculate? And we look at it through the lens of, if we're trying to denitrify, how much should I recirculate? There's no good model right now for knowing how much nitrate you're going to be able to remove within a polishing cell. Within an anoxic cell. And so, we're trying to develop that right now is our goal, right? And this is why we're studying this. This is why we're getting communities that are interested in this to come on board with us and do a study where we get some more data to try and model this, eventually create a model. But we sat down at the beginning of this process and we said, okay, let's just say theoretically, we could accomplish maybe say 25% denitrification, 50% denitrification, 75% denitrification, right? Given these assumptions and based on different levels of flow, recirculated flow, what do we expect to see out of the effluent? So this is, totally gross model. This is a lot of variables, so on. We totally get that. We're just trying to get a ballpark here. And what this really told us, this analysis was, in any circumstance, whether we get 25% denite, 50, 75%, the more we recirculate, the better chance we have of getting lower total nitrogen or total inorganic nitrogen. And makes sense, right? I mean, you have to give the bugs the nitrates, right? And the more you recirculate, the more nitrates you recirculate, because all your nitrates are at the back of the plant. They're not at the front of the plant, because at the front of the plant you got ammonia, and then you nitrify, and then you got your nitrates at the back. And I think that this principle of recirculation is true with when it comes to BOD removal, when it comes to ammonia reduction, all these factors. The more you do it, the better. I think there's probably a limit. I don't know that we would go above 100% of your average daily flow, but for any length of time. But at this point, we're just modeling up to 100%. So why blending? Well, and this picture here is it's nothing to do with blending, but the reason I'll say this, it'll become clear why I have the picture here in this picture in particular. So before I get there, so blending of recirculated water with the influent water creates the natural mixing of the higher DO, high nitrate water coming from the back of your plant with the low DO, high BOD water coming from the collection system. And it's really trying to get a very adequate mix of all that, of both those waste streams to the front of the plant. So by the time it gets in the lagoon, it'll be low DO, it'll be thermally regulated, equalized. The warmer water from the collection system will blend with the colder water from the back of the plant, and it'll hopefully lower the DO altogether. So now, why this picture? So one of the things we do here is we rent mobile treatment units, these little frac tanks, little frac tank MBDRs. And this was a project that we did a couple of years ago. And it was at actually, interestingly enough, at a fertilizer plant that had too many nitrates. Go figure. They were generating nitrates and they had too many of them, so they want to get rid of them, which sounds kind of weird, but they couldn't capture them once they got into the stormwater system, so they had to get rid of these nitrates somehow. So they had some ammonia, so what we did was we had the nitrification tank there on the left, the denitrification tank on the right, and we ran the system. And we're running it, and then the water came out of the back of the denitrification tank, flowed 500 feet to a storage lagoon, and boom, it was done, right? That was supposed to be one pass, done. So we started the system up, and we were having all sorts of issues with pH and all these different factors to get nitrification, get the denitrification to work. The DO was too high, and all manner of things. We learned a lot on this project. Eventually, we sorted out all these issues. And what was really interesting was the water coming out of the denitrification reactor as we pulled a sample on the exit to it was, let's say, 30 milligrams per liter of nitrate, right? But then it went in this pipe, it went all the way to the lagoon, and then the water coming out of the pipe at the back end of the lagoon was, like 5 milligrams per liter nitrate. And so evidently, this, between coming out of the reactor, and granted the reactor was too high in DO, we had a really hard time getting the DO down, and coming out of the pipe at the back, the DO was plummeted down to under 0.5 milligrams per liter, and so did the nitrate. So we were getting denitrification in the pipe from the back of the reactor to the lagoon. And that whole thing just stuck with me for years until we got to this point. I'm like, man, maybe we can get some Denite in this pipe when we blend this influent waste stream with the recirculated waste stream, and at the very least we can get some DO breakdown on this thing. So that was sort of the genesis of that idea. I thought I'd just share with you. Kind of interesting. So why an anoxic zone? Well, in order to denitrify, we need to have low DO. And again, that was going back to that project. Learned a very hard lesson on that project, which is you don't want to be in a position where you're trying to denitrify with high DO. You need under 0.5 milligrams per liter DO to really sufficiently denitrify. So this is a survey of a plant we did, and I'll talk a little bit more about it later, where we go in there, we do a sludge profile, and we do a DO profile. That was me in the boat at the beginning of the class in the agenda slide, literally right there. And pretty nasty business being in that boat with the sludge judging and such, but somebody's got to do it. And so as you can see here, a couple things that you'll notice here. First of all, like this particular zone, obviously non-aerated, true anoxic zone. DOs overall under 0.5 on average. Pretty good DO profile throughout the water column to do what they want to do with this. And you'll see that some of their data, they did pretty well. Second thing, they had sludge thickness. They did have some sludge blanket. This system was more recently desludged. But within an anoxic zone, because it's not mixed, or it can be mixed, but in this instance it's not, they had some sludge deposits, and actually the sludge deposits can actually help to depress the DO a little bit more. And in many cases, the pipe coming from with the recirculated and blended flow is coming into a sludge blanket, which is a good environment in order to get those anoxic conditions that you need. So it's really the water's kind of emanating from the bottom and coming up to the top. And so, you do get that benefit of low DO in order to get the denitrification. The other thing, if you don't mix the anoxic zone, which does come with it a little bit less denitrification efficiency, most likely, is that you accumulate your sludge in one spot, and it's more easily removed from one spot rather than it being distributed throughout your entire lagoon, which makes it harder to remove. So mixing, and this is something that we've done a little bit of in some of these studies, and we're going to do more of and learn more about. But I like this this guy changed my mind. Mixing is the solution to 90% of lagoon problems. Changed my mind, and I believe this is true. 14 years of doing this. Usually if you can get good mixing, you can get the bugs. You can get the food, and if you're aerating, you get the oxygen. all together in one spot, and you get more efficient removal of everything, of sludge, of BOD, of ammonia, of whatever it is, anaerobic, aerobic, it doesn't matter, you know. Anoxic mixing is always a good thing because you're combining the microbial community and you're keeping these solids in suspension so that the bugs can really break down things in a more efficient way. So this is a little mixer, a little garage-made hack by yours truly. This is not my finest hour, but you know, we were testing this out, and basically you have a hose which connects to this manifold here. You know, it's obviously a complete pilot hack job with some jet nozzles on the end of those two T's. And again, the idea is to blend the water, shoot it through a mixer so that you get this static mixing, pumped mixing going, and you're really trying to keep those solids and the oxygen, sorry, not the oxygen, the solids, the nitrate, the BOD all in suspension, all working together so that it can get the most efficient denitrification possible in the least amount of space possible. One other thing you can do that we have seen, and this again harkens back to kind of taking a page out of the activated sludge book, is that you can cycle air. So let's say you don't have an anoxic zone and you still want to see if you can get some Denite. You could literally just cycle the air in certain zones on and off for a period of time in order to get, you know, aerobic and then anoxic, and then it goes anaerobic. But you don't want to go all the way anaerobic. You want it to go aerated, aerobic, turn off the air, go anoxic, and then turn the air back on. And that gives you the benefit of getting some mixing while also, you know, keeping the same treatment zone, the same, you know, to move aerators or do anything like that. So in our case, and, you know, we haven't done this before, but, you know, we would do, if we were to do it, would be to, we have these individual airlines on these manifolds going to each individual aerator, which for us is, you know, each airline has its own ball valve, so you can control the airflow going to each aerator from this manifold, which is really helpful for an operator if they need to move air around a lagoon. You could simply just put a valve controlling the air to the whole manifold, and you put a valve on a timer, right, so that it would turn off the air to that manifold, leaving all the other air going on the rest of the system, and then open it back up after a certain period of time. So that's another possibility and something we're going to experiment a little bit more with over the coming months. Covering. So that's one of the other things we can do with a system. Like I said, DO is such a critical metric when you're denitrifying that you really don't want any of it. You want about 0.5 to around 0.1 or even a little bit lower than that. You don't want to go anaerobic, but you don't want to go aerobic. And so most lagoons get their DO from wind blowing across the surface of the lagoon, and that atmospheric contact of the top of the water with the ambient. And so by covering it, you're able to get, obviously, just prevent that. You also get other benefits. You eliminate algae growth and so on. And so, you know, if you look at this DO profile, this is kind of what I showed you earlier, that these B5, C5, A5, right, these are all within the first 2 feet of the water column, and you can see they're all up in the 1 milligram per liter dissolved oxygen range, which is fairly typical of what we see with lagoons. You know, you're going to get some, especially stagnant, non-mixed lagoons, you're going to get, you know, higher DO at the top, lower DO at the bottom, right? And so you can actually cover it. So we've actually found this product that we're starting to partner with the manufacturer on, which is essentially a hex tile, which you can put on your lagoon in order to, you know, you just throw them out there, frisbee them out there, and they all kind of interlock together, and a pretty easy way to kind of dampen DO. And if you were to put a mixer in an anoxic lagoon, then you think about putting a cover on that, because, you know, more mixing would exchange more water at the surface potentially and cause more DO. And so, you know, covers can be helpful, and we've done a few of these in the past, and I think we're going to experiment with this in terms of the anoxic zone shortly. So our standard kind of suggested operating steps, optimization steps would be, first of all, recirculate, right? Just start, if you want to get DO from, let's say, your last pond to your middle pond, or if you want to put DO somewhere, you can recirculate. If you want to reduce algae in your second pond because you're getting a bad algae problem in your second pond, then recirculate from your third pond to your second pond. So just start that. Now, if you're looking to do Denite and get a little bit more serious with it, then, recirculate to the front, recirculate to an anoxic zone, blend the influent with the recirculated water, add a mixing to the anoxic zone, add a cover to the anoxic zone, and then if that's not giving you enough, then you can look at the aeration zone if you have one that's after that, start to think about cycling the air in that aeration zone to see what happens. So a couple of case studies here. First one, this is a facility, our company, if you didn't know, we just recently moved to Colorado, and this is about 3 hours from our Colorado facility. This system has been online for quite some time, and they've actually coincidentally already had an anoxic zone, and I think the initial intent of the first lagoon, because they didn't have recirculation design into the original design, was more to settle solids and essentially be a screen to the aeration system, right? Basically be a sinkhole for rags and trash and solids and everything else that might come into the plant. And so they already had that, and then it goes from there into the aeration cells, which are one lagoon but 3 cells baffled. Then from there through a nitrification reactor, then from there through a polishing pond and out to the effluent. And so this plant has actually been operating for a good 10 years, 12 years, and been doing quite well. It was primarily designed for low BOD and ammonia, but more recently they got a total inorganic nitrogen limit put on them from the CDPHE, the regulator here in Colorado, and so they're trying to figure out what to do, right? And so the plan that was come up with was to recirculate. This is actually initially wasn't our idea, it was CDPHE's idea. And what we're going to do is, or what we have been doing, is come out of the reactor and then recirculate back to the headworks building, A, where water will be blended with the influent water and flow through the existing pipe into the anoxic zone through cell 1, cell 2, cell 3, aerated back through the reactor, recirculated, and or go through polishing and ultimately out to the effluent. So this initially for Oak Creek is a pilot, and so we kind of help them to put a recirculation system in. It's only temporary. The main goal here is to get through the winter, this winter, and prove that they can achieve their TIN limit of 13 milligrams per liter. And so we got 4 pumps, and this is coming right out of the reactor. It's where the water dumps in from out of the reactor, goes through our system here. We've got one line that will go up to the front of the plant, so I'll show you in another picture here in a minute. This line actually goes back into the lagoon. This is just a bypass line just in case we need it to basically bypass the blending mechanism later on. So the water comes up, flows all the way down the berm, down to the building up here. It comes into the building, the influent building right there. We actually we redid this influent recently, and I don't have pictures of it right now, but you get the point. It's coming in, it's being recirculated back to the front where it's blending with the influent water, then flowing through the pipe and getting put into the anoxic zone. So we've only been doing this study for about 3 months, and we haven't been operating at the level of recirculated flow that we want to get to. And so we've been, most of the time it was at 25%. About a month ago, we increased it to 50% recirculation flow rate, and we're trying to get it to 100% as soon as we possibly can. But nonetheless, what you'll see here is that the data we've collected so far is excellent. We are seeing extremely low numbers out of the system, average of 3.2 BOD, 1.29 ammonia, and 12.59 TIN, with just 25% of recirculated flow, and more recently we have one data point with 50%. So it's already seeing the benefits here across their system of recirculating the water. This shows you on a data point by data point. The last graph was for average, the data point by data point here. A similar story. As one thing I'll show you in subsequent slides here is that they were flirting with their 13 limit right around 15 TIN, and then as soon as they started increasing the recirculated flow, they dipped below 13. I got another slide on that, so I don't want to steal my own thunder. But BOD and ammonia has been extremely good as well. They're well below their BOD limit. Obviously, they're putting out basically nothing. This shows you, and this is what I was referring back to with the previous slide, where you look at the different forms of nitrogen. And this is a stacked bar looking at total inorganic nitrogen based on what form that is in, right? So in the influent, like I said, it's all ammonia, basically. There's a little bit of organic nitrogen in the mix here, but there's really no nitrate in the influent. And this is why you have to recirculate, right? Because as you move through the system, the lagoon does a little bit of nitrification here, right? And then it goes through the reactor, and it's like, boom, no ammonia, 100% nitrate, right? Makes sense, because the reactor is designed specifically to nitrify, right? And so then you've got to take that nitrate and you've got to put it back to the front of the plant where you can get denitrification in the anoxic zone, right? And so what we have found with the system is that the nitrates that we're putting into the anoxic lagoon are getting destroyed pretty readily, but we're not putting, based on this data, we're not putting enough in there, right? Because we're only been recirculating 25% and more recently 50% to get a lower inorganic nitrogen level below, to have it drop even more. And so as you can see, still what you find at the outfall is that most of their TIN is nitrate. And so the recirculation, the more we recirculate, the lower and lower that number is going to be. And it'll probably still end up that way in the wintertime, because it's going to be easier to remove ammonia through the reactor, which is specifically designed to remove ammonia, than remove nitrate in cold weather. But we are really looking to increase that recirculation rate, because we feel like that's going to give us lower overall total inorganic nitrogen. And this, again, we've only got a couple data points here. Apparently labs have been struck by COVID as well, and just like everything has slowed down because of COVID, logistics, supply chains, labs have also slowed down. So you'll see here the last data point I have is from the end of September, which means it's been an entire month of October, and I still don't have another data point from 2 data points that I need in order to get a better progress update. But I digress. This graph clearly shows that as you increase your recirculation rate, you decrease your effluent nitrate. Again, makes sense. You've got to take those nitrates and you've got to put them somewhere where they can be destroyed. The more of them you take, the lower the nitrate you're going to get, because the more of them are going to get destroyed, right, by denitrification. So our goal here is to get up to 100% of Q. We just started up the recirculating blending mechanism, so we want to get that online and get that stabilized, because we've just been recirculating up to this point without blending. And so we're hoping that we run over the winter and we're going to get pretty low nitrates and maintain their TIN under their limit for the entirety of winter. So second case study, Mission Hills, California. So this is actually a client of Steve Harris, and we recently started working with them on this. They actually already had a recirculation system in place because they're awesome, and they had some elements of this already there. So the initial anoxic lagoon up here, followed by aerated lagoons, followed by a post-anoxic lagoon with their effluent and recirculation. Interesting enough, me and my colleague Shakti flew to California, and we got upfront and personal with some wildfires, and it was completely gnarly. We had smoke in all around us. We had, as you can see from the plane when we flew out, this is the picture we took, and then when we got on the highway, the coastal highway there, we got stuck in a wildfire traffic jam, and it was scary. At one point, literally, you couldn't see anything around me. I looked down, I could see the line, the white line on the left-hand side of the road. That was the only way I knew which direction I was going in. So, again, lagoons do it better. I stop at nothing to help lagoons do it better. Going through wildfires is part of that. So this picture here on the left is their anoxic lagoon. The picture here on the right is the water coming from their effluent that's being put into that manhole, where it blends with the influent water coming in, and then eventually it finds its way to the bottom of the corner of the anoxic lagoon, the near side corner that you're looking at there. So similar story, very, very good average lab data with this system. They really are doing a fantastic job with BOD, with ammonia and TIN. They're hitting numbers that are very low. I mean, their TIN is 9.49, which, total nitrogen, which is pretty darn good for a lagoon on average, but they've been hitting numbers closer to 5 in some instances. So this kind of tells you a similar story to what I was showing you before. This actually looks at their effluent. So unlike Oak Creek, where most of their effluent total nitrogen is in the nitrate form, for Mission Hills, it tends to be in the ammonia form. And the reason is because they're not getting complete nitrification because they don't have a nitrification reactor. They are getting some within their lagoon system, which is great, but they're not getting it as much as they need to in order to get their TN. So their real limiting factor here to get their TN below 10 or below even lower than 10 is really the fact that they're not nitrifying as much as they could be, as they should be, or they can be, because they're trying to do it in the lagoon. And so that's where the nitrox reactor or similar reactor comes into play, where it's very, very good at nitrifying and getting rid of all that ammonia. Otherwise, they would really be crushing it even more than they already are. So with them, we're planning on taking some next steps here in the coming months to increase their recirculation rate by 50% and to try and get more of their denitrification happening within their anoxic lagoon by just putting more water to the front, giving it more nitrates. And we really feel like that's going to further improve their nitrate reduction. And then, we want to turn some aerators on in their secondary and post-anoxic cell. They actually already have aerators in there. And by putting air mixing in that post-anoxic cell, we're going to be able to get more nitrification potentially, and ultimately, obviously lower their TN, because most of their TN is in nitrification. Is in ammonia. So just some takeaways before we get on the Q&A here. Lagoon recirculation is a very cost-effective way to improve overall treatment performance. Like I said, my general observation is about 10-20% benefit to any metric, BOD, TSS, ammonia. Recirculating along with lower BOD, lowering BOD improves DO, reduces algae, helps to lower TN and ammonia if you use anoxic zones, or even if you don't, you're likely to see some benefits with TN and ammonia. A dedicated anoxic zone is the most ideal if you're trying to get rid of total nitrogen and get below 10, which is where most limits, if you have one, are at. And then the higher level you recirculate, the better overall results you're going to get. I wouldn't advise going over 1Q, but certainly anything up to that point would really improve things. So with that, any questions, if you can put them in the chat. Eve is going to share those with me. curate and share those with me, and I'll try to answer what I can right now. We got about 5 minutes left. Otherwise, my name and phone number's here. And if you guys have any questions, you can feel free to email me or call me, and I'll be happy to help in any way I can. And we are looking for other sites that are interested in doing denitrification with recirculation. So if you have a limit or have a need or have a desire, or just a general lagoonatic who just loves tinkering around and making your system better, I'd love to talk to you, because we'd love to be a part of that. Okay, so questions here. So somebody was asking here about, does it not, recirculating 1 cube back to the front of the lagoon, does it not affect the hydraulic retention time? And again, this goes back to that slide where I was talking about circular logic. It's sort of confusing, but at the end of the day, because all lagoons are set up with a certain hydraulic volume, right? Even if you're recirculating within the lagoon, right, what comes in must go out, and it's going to be equal, right? You can't, you're not increasing your daily flow by recirculating. Your daily flow stays the same. You're just moving that water around the system more frequently. And so again, it's sometimes it's a little hard to get your head wrapped around, but at the end of the day, like, the system's going to stay. What comes in must go out. No more flow is going to go out than's coming in. No less flow is going to come in than's going out. It's just, minus some evaporation and things like that. But, it doesn't change your overall flows. The HRT stays the same because you're just moving water around from within the system. I hope that makes sense. So somebody was asking, if you recirculate from the back to the front, are you not cooling your influent down? And in so doing, affecting your biomass, effectively slowing down your biomass at the front of the plant due to cooler temperatures. That is true. You are cooling it down, and you will see a minor loss in biological treatment efficiency by just having colder water potentially at the front. But as I think about this here, if you lower the overall temperature, but it's really not something that, most lagoon systems from a biological perspective are designed for the worst case winter temperature. So when we design a lagoon, for example, we essentially assume that the water in the lagoon in the winter in a northern climate is going to be 0.5 degrees C, right? So basically just shy of an ice cube, right? And so our biological sizing and treatment calculations assume that worst case condition, as if that's happening the entire winter long, right? The fact is, yes, you slow down the biology maybe in the summertime or maybe in other times, but your entire hydraulic retention time is designed around a worst case temperature condition that even if you recirculate in the winter, you're not going to see. Or if you do see, you'll be fine. And so it's really not as much of an issue from that point of view. You'll see maybe a slight reduction in the overall efficiency, but you're supplying the bugs with more food, which because you're taking BOD from the back and putting it in the front, those bugs you're growing more bugs because they're eating more food, which is bringing on a mass balance basis, you're still going to get lower BOD by recirculating than by not. So I do see that point in the question. We have not done any studies on facultative lagoons. The trick with facultative lagoons is they are shallow, and so dissolved oxygen, that first 2 feet of water makes up a significant amount of volume of the total lagoon. And because that first 2 feet of water is, going to have more algae in it, which is going to grow, add more oxygen to the water, and because the first 2 feet of water is a big volume and tends to have higher DO, it's going to be harder to see some of the anoxic benefits associated with this unless you cover a section of your lagoon in order to avoid the algae growth and avoid that surface water transfer, surface to surface transfer. But we haven't done it in any facultative lagoons quite yet. What is the ideal recirculation rate? Is there any basis or formula for calculating of the same? So again, we modeled this a little bit with our kind of very crude model that I showed you on one of those slides. And in our view, 1Q is the more you recirculate, the better, and up to 100% of your average daily flow is generally better. You can do as little or as much as you want, but the more you recirculate, the better benefit you're going to see. So I mean, in terms of what's quote unquote ideal, I just don't know, because we just don't have the data to show that. But in our analysis so far, it seems like 100% would be good. Okay, with that, I think we'll wrap up here. If you have any more questions, again, shoot me an email, or you can respond and shoot Eve an email that was part of the invite. I'll be happy to answer them later. We usually do. We do have a survey after this. It'd be really helpful for us to get some feedback on what you thought of the webinar, how it could be improved. It's just really helpful for us, because we don't want to waste your time. We don't want to waste anybody's time. We want to give them the best webinars we can, and so the feedback is really helpful for us to optimize the benefit here. If you could take a few minutes to complete that, I really appreciate it. Anybody who wants CEUs or PDHs, we did get some CEU approval from states that responded to us within the time frame here. We'll be happy to provide those certificates for you, or the documentation necessary. PDHs, very happy to provide those. Again, you want to email Eve at lagoons.com about those PDHs, and she'll get them out to you. It's pretty quick and simple. Well, thank you guys very much. I really appreciate your time today. I hope you enjoyed the webinar, and we'll hopefully I'll catch you at the next one coming up here. We have another webinar coming up in a couple of weeks, and look out for emails for that. Thank you very much, and I'll speak to you later.